Okay, thank you very much. Good afternoon, everyone. So this is part 3 of the 3-part webinar series on die casting design. And today we're going to focus on what should be die cast. And so again, let me just go through, hopefully everyone's familiar with this by now, but let me just go through the screen here. You can open and close this panel hitting this orange button. So if you hit the orange button, you close it, and then if you hit it again, you open it. And the reason, again, I'm telling you this is so you can ask questions. We've had quite some questions over the past couple of weeks or so. So if you have a question, something I'm talking about is not clear, you can fill it out real time down there where it just says enter a question for staff. If I can find my cursor here. Oh, there we go. Enter a question for staff, and then just push send, and then we get it. And you can do that real time during the presentation, or you can do it at the end, because we're going to address all the questions at the end, as we have done in previous weeks. Again, here is the people who are sponsoring this, and again, you're all going to get copies of this webinar brought to you by these people. So Daco zinc die cast in Chicago, white metal, aluminum, magnesium, and zinc. Technical die casting, aluminum and zinc, Lakeside Casting Solutions in zinc, and Similex, aluminum, magnesium, and zinc. And again, we're going to talk in detail about having conversations today between designers and die casters. So again, these guys clearly are interested in talking to you, but if you want to find someone a bit more local, you can go to diecasting.org. And that's the main website for NADCO, and there's a directory in there of die casters, and you can find people who would be very happy to talk to you about some of the things that we've been discussing today, but obviously they'll talk to you in a lot more detail about them. So again, this is really the focus of the talk. Again, I probably don't need to go through this in detail, but basically what it's saying is that design can account for 70% of the cost of a product, because 80% of the quality problems are unwittingly designed into the product itself. And so what we're going to talk about today, because if you don't understand the process, then you're going to create designs that are not ideal for the die casting process. So the goal today, we're going to talk about some kind of general broad stroke ideas. Again, they need to be developed more by discussing them with your local die casters. But we're going to talk about what makes a good die casting and what makes a bad die casting. So this is going to be the focus of today's webinar. How do we design for die casting? We're going to talk about what features can I die cast, and in fact, what features should I be die casting. So this is the outline of today's talk. We're probably going to spend about half the time today talking about optimizing geometry in terms of the necessary features we need to add to a casting to make it a product that we would like to die cast and makes it easy to die cast. In terms of to take the current design and modify it so it is die castable. Then we'll talk a little bit about secondary operations in terms of assemblies, machining, surface finishing. And then finally at the bottom there, one question that often comes up is how do we prototype die castings, and we'll talk about that and give you some ideas on how to best approach that. And again, as we've talked about, a good resource, fantastic resource really, at diecastingdesign.org. Lots of resources there in terms of how to design for die casting, and we'll address some of these today. And also the book we talked about, and then the product design for die casting. So starting with geometry optimization. What we're trying to do here is basically take the component that's shown here on the left-hand side and change it to a die-castable component shown on the right. So if we look at the left-hand side design, there's a lot of features missing that we need. It's also a poor die casting. It's probably an easy part to draw, but not very easy to die cast. So it's really not a good design for die casting. So we need to understand draft, fillets, where I'm going to put the part in line. We'll talk about bosses and ribs instead of having solid features, i.e. the right-hand design rather than the left-hand design. We'll talk about holes and windows and how we handle those in die casting. And that really kind of takes us to what we talked about on the last webinar in terms of how to get uniform walls. Casting is absolutely a fantastic process, but certainly we're going to generate more porosity and more defects when we have a large variation in wall thickness. And this is not just true for die casting, it's true for all types of casting processes. It's based on how the metal solidifies, and most casting processes are going to struggle with large variations in wall thicknesses over big areas of the cast. So what we're really driven towards here is thin rib features, again, such as I'm showing on the right-hand side here, rather than the solid thick wall component shown on the left-hand side. Then finally, we'll talk a little bit about how to order these features in your CAD software so we can, or you can avoid messy drawings that from time to time may crash and cause those kind of problems. So ultimately, the question we're trying to answer is how to take the optimized geometry on the left and then change it to something that's die castable on the right, and therefore improving the casting performance. So shown here, we've got the optimized component on the right. We're using much less material, so therefore we've improved cost, because obviously metal is cost in the part. It's also going to be lighter, but most importantly, the right-hand side, we're going to get a much better quality die casting, and more importantly, you as the customer is going to get a much better quality die casting, much higher quality casting overall. Now, if any of you have worked with die casting before, you'll know that the first thing that we've got to do is to add draft to the component. So we need to add draft on every feature that's perpendicular to the parting surface. And the reason for this, it's pretty clear. This allows us to open the die without dragging on the surface of the casting. It also allows us to eject the casting, to remove it from the casting die without putting undue stress on the casting. It's going to prevent the formation of drag marks on the surface as we open it, or actually even bending the casting, or ultimately even fracturing the casting. All those can occur if you don't get draft correctly. So when we have draft, we have the ejector pins. They push it forward just a little, and then after just a little bit of motion, all the surfaces have moved away from the die face, all the cast surfaces have moved away from the die face, and then ejection can occur with no further resistance from the die. So in the ultimate case, if the casting doesn't eject easily, we'll certainly push the ejector pins through the casting. I've certainly seen that happen. The casting is still very hot, it's weak, so it's really easy to do if the casting is sticking in the die. So we need adequate draft for all operations to go easily. So draft is going to improve the surface quality of the casting. It's going to also improve die life. The die is a very expensive thing. We want it to last as long as possible. And so with draft, we're not going to be so aggressive when we're opening it, when we're ejecting the casting, and so the die is going to last longer. Couple of rules when we look at draft. Draft is going to be different for an inside wall versus an outside wall. So the reason here, if we look at the casting, this cylindrical part shown here, so as the casting solidifies and shrinks and cools, the outside surface of what I'm showing here is going to shrink inwards, and so it's going to pull away from that outside die wall. But if you look at this inside surface here or the inside surface here, these two are going to shrink inwards, but they're going to shrink towards the die surface, and so it's going to shrink around that feature and grab on an inside feature rather than an outside feature. So we tend to need more draft on these inside features than we have on the outside. Excuse me. We also need more draft on holes and windows for the same reason, and we also need different draft on chord holes. And we'll talk about those a little bit as we keep on going here through today's presentation. So when we talk about draft, we're often talking about two different levels. If you go to diecastingdesign.org, you'll see there's a standard level and there's a precision level. The standard is for not particularly high performance castings. We can get away generally with more draft on those castings. It makes them easier to make. But as I go towards higher performance castings, or maybe applications where I need a greater level of control over the casting, then we start looking at the precision level of draft, and that allows us to use, or requires us, I should say, to use a lower level of draft. So this is the information that's actually available at diecasting design.org. It's also in the die casting design book. And this information gives you a couple of equations you can see here on the right-hand side there for calculating the draft angle based on the depth of the feature. And so this is obviously really, really useful. It's used by die casters, but it can be used by you as designers also. And at the bottom here, we have values for the constant C. L is the length of the feature. C is the constant shown here. And you can see it's different value for different metals being cast, inside walls, outside walls, and holes. Now, most CAD packages, of course, will do a draft analysis for you, and you can get a color coding, you can get green or yellow or whatever to identify different parts of the casting. So this helps us identify where the parting line should be, and I'll show an example in a second how features need to be produced with slides in terms of a side action pull. So this also helps to show where flash is going to show up. Obviously, flash is going to show up where we have parting lines. And so it's very helpful for design people such as you to do this kind of draft analysis even before talking to the die caster, so you can get an idea of what features are going to require drafts and therefore how the tool is going to be built. And so that's going to help simplify the die design process. So here's an example of a knob. And on the middle there, we've done a draft analysis for a 3-degree draft, and the draft on the yellow surface, this shows where we have less than 3-degree draft. However, if we change the analysis to half-a-degree draft, then the yellow goes red, and we can say, yes, now we've got more than half-a-degree draft on those surfaces. Then we can get more complex. We can start looking at parting line arrangements, and we can adjust where the draft analysis is applied. So in this case, yellow is parallel to the parting surface. Red is one side of the parting surface, and green is the other side of the parting surface. And we can start evaluating different designs, looking at different positions of the parting line. So if we look at this casting, clearly we're going to need a slide. We've got these two windows here, and that's kind of facing us here. These are basically metal savers, and obviously we're going to need a slide to produce those features in the casting. So this is obviously helping the designer to understand how the casting is going to be oriented in the die. It's going to be very helpful in terms of thinking about gating, in terms of how we're going to get the metal into the cavity, some of the things we talked about in the last webinar. Excuse me. And so the next thing we need to look at is fillets, and basically, how do we make the part more applicable for die casting? You can see we've taken the upper component and filleted all those sharp corners. And so fillets are needed basically on all sharp features and all sharp corners except for the parting line. We don't have to have fillets on the parting line. We can have sharp features shown here. And you can kind of see on the bottom here. So the parting line, if I can get my mouse to work again, the parting line is down here on the bottom. But we've filleted all the other surfaces. So the advantage of fillets, it makes the part stronger, but most importantly, it significantly improves the die life. Again, the die life is obviously really, really critical. Sharp corners in the die are going to be stress risers. If we fillet them, we remove them, and therefore we're going to remove the stress concentrations, we're going to remove the heat concentrations in these corners, and so the die is going to last much longer. There are some disadvantages of fillets that basically we just have to live with. Firstly, sometimes we can create some locally thick sections. Basically, we're often adding material, and this can make sections thicker and therefore can have localized porosity in these areas, and we'll talk a little bit about that in the next few slides or so. And obviously, sometimes fillets can be difficult to apply to complex geometry. So those are a couple of disadvantages of fillets, but again, generally, we just have to live with that. So this is the books from some information, I should say, from the book, the product design book. It's also on the diecastingdesign.org website, and it shows examples of optimum design features for different features, but we're shown here for fillets. So generally, what we have is a not recommended, a less desirable, and optimal. So here, for a fillet, You can see here we have a sharp corner. We don't like that. We just talked about. Here we've just got rid of we've got the fillet on the inside, got rid of the sharp corner on the inside. But now we've got a heavy section here, so we'll get shrinkage porosity in that area. And the optimal design is shown here when we got uniform wall thickness all the way through that fillet. Doesn't have to be same thickness. Can be applied to non-uniform walls, but again, not recommended with sharp corners, less desirable. We've now got the heavy section here, and most optimal, I should say, is again trying to keep the wall change at least as uniform as possible. We can do that for crossing walls. Again, the same kind of thing we just talked about. We can do it for fins and ribs, and again, you can kind of see here, we tried to keep, for the optimal design, we tried to keep the wall thickness as uniform as possible. Now, as I said earlier, parting line, when we look at parting line, this is the only place that we're actually allowed to have sharp corners, and this is basically going to define the inside and outside of the part. And as I talked about, the draft requirement is going to depend upon whether we're talking about the inside or an outside surface, and then we can apply draft, and then we can apply fillets. Now, as a feature, we much prefer die casting bosses, much prefer the boss kind of thing shown here than a heavy section. Obviously, we could make this as a solid piece. Firstly, it's going to have a lot more metal in it, and secondly, it's going to be a huge heavy section, and we're going to end up with tremendous shrinkage porosity towards the center of that. So a boss is a much better feature, now pretty uniform wall thickness all the way through this, and so this is obviously some kind of a round casting, maybe a knob on a stove for turning on the gas. And so we much prefer to make this as a hollow cylinder with a boss in the middle. Excuse me. Bosses are also useful if we need standoff, for instance, for intricate electronics, we can use bosses. But again, as we've talked about, we're going to need a draft on the bosses. Sometimes these kind of bosses can be a bit problematic to fill, so in that case we can add ribs, and that helps us with the filling of the liquid metal. So here you can see we've added ribs to the inside to help feed the liquid metal to that boss, and often it's quite useful to think of ribs and bosses as a package deal, certainly when you need to go in, as we just talked about, to remove material to have the thin wall casting that we like for die casting. So we core the features, and then we have ribs around it to increase strengthening, keeps the walls uniform, helps the metal flow, helps to get the liquid metal into the cavity, into the boss. But again, we need to add drafts and fillets to obviously both the bosses and the ribs. But one thing that's kind of important to keep in mind is that, as I just talked about, one of the best ways of saving money to reduce cost is don't add excess material. If you can save metal, you're reducing the amount of metal that's in the casting, so you're going to reduce the cost of the casting. So don't add ribs where it's not needed. So another example is that by adding ribs, we can unwittingly add a problem. So for example, if we look at this casting down here, we've got ribs, we've got the bosses, and so down here we're going to have some remote thick sections, and we're going to get porosity in those remote thick sections. So if I have a casting that I cannot tolerate any porosity, if I add ribs where I don't need them, I'm going to introduce quality problems that I could have avoided. Talked earlier about holes and windows, and often these are features that can be quite difficult to fill around, and then often can be quite difficult to eject the casting. What happens is the casting tends to grab around the window, it shrinks on the window, and as we talked about earlier, we need lots of generous draft. And often we require more draft on windows than any other features on die casting. So what people do often is use bridges across the windows. Possibly that's what's shown here. Maybe this is one long window in the original design, and we put bridges across it to allow the metal to flow from one side to the other. And then another thing that some of you may have heard of from die casters, if we want to flash across the window. And so what we can do is we can add a 10 or 20,000 bridge across the window and then trim out that flash afterwards. And again, that helps the metal flow from one side to the other side across the window, and also helps prevent sticking in the die during ejection. So if we design a casting that's got a lot of windows in it, which often electronic components can do that, then we need to be concerned about ejection. And so here we've kind of talked about ways to try and avoid that. Let's just talk a little bit about symbols, letters, logos, whatever, on the casting. This is something that we do very, very well with die casting because we're using a steel die, and so generally the letters are very, very sharp on die castings. What we want to do, though, is always we want to raise the letters. We want to raise the letters above the casting surface. As you can see here, we never want the letters depressed on the casting surface. And the reason is that we want to have the nice sharp letters we just talked about. That's one of the advantages of die casting. We don't want this sharpness to wear away over time. So what happens if the letters are depressed on the casting, then they're going to be standing proud on the die surface. As the liquid metal flows past it, it's going to erode away those corners, and so the letters are going to become fuzzy over time, and the sharpness is going to disappear. So we always want letters, logos, etc. standing proud on the casting surface. If we do need letters to be depressed, then one thing we can do is raise them on a depressed panel. So the example shown here for the knob, what we can do is put a raised periphery, a raised rib around the periphery, and then the entire internal side of the face becomes depressed slightly, and then the logos can then stand proud on that depressed face. They're still going to be below the peripheral rib, but that's a good alternative, again, a good way to keep the letters sharp on the die casting die. Now, as we talked about, the ultimate goal is to obtain uniformly thin walls in our die casting. We've kind of talked about this at quite some length over the past 2 webinars. But keep in mind that there is a lower level to how thin I want to make the walls. Uniformly thin walls throughout the casting. If I go too thin, then I may need too high a metal velocity to fill the casting. Too thick, we're going to increase cycle rate. The casting is going to take longer to solidify, and it also may introduce defects, some of the porosity that we talked about in the second webinar. Now, there are some CAD packages that can do this analysis showing the thin sections of the casting. And NADCA also sells a software. It's called CastView. I like it. I use it quite a lot. It's a very low-cost program. Quickly identifies the thin sections of the casting, and that's kind of what we're showing here. So what we've done here is mark the areas in green that are below some critical thickness. And it shows a couple of things. So we can see where areas that are thicker than a critical thickness, and we see where the thin areas are that could be a problem to fill. Now, excuse me, as I get very thin, 2 problems do show up. For thin sections, generally the metal velocity, the velocity we're filling the die tends to be very high, and so we can get erosion of the die steel, of the casting die itself, and that's kind of what we're showing here in the photograph. We can kind of see here that the surface of the die is not as good as it is away comparing it to areas over here. And what's happened is that in this area the liquid velocity is very high of the liquid aluminum, for example, filling the die. It's eroding away the die steel due to this extremely high filling speed, and it's given us die life problems, and probably with this die we'll have to replace it earlier than we would really like to. We can also get cavitation during die filling. This often happens, again, when the injection speed of the liquid metal is too high. It's going to occur with all the metals, aluminum, magnesium, zinc, and it's very similar to the cavitation you get within a marine propeller, for example. And so here's a good illustration. You can kind of see the area marked here, cavitation. This is on the actual die casting. And what happens is that this is just a mirror of what happened on the die casting die. The injection velocity of the liquid metal was so high, we got cavitation bubbles, and these bubbles implode explosively with very, very high forces, and if they do that against the die surface, it's just like shot peeling the die surface. And again, we're minimizing die life, and we're going to have to replace this expensive die faster than or earlier than we would really like to. Now, we also want to try and avoid thick sections in the casting. We've talked about this a lot. Again, software is available to identify these thick sections. Maybe a package can do it. Again, this is CastView software that's available from NADCA that quickly identifies the thick sections in the castings. And these will be areas that tend to going to have porosity in the die casting. And I use CastView a lot to try and identify areas, the thick sections where porosity is likely to occur. I find that very useful to do. Another problem with thick sections in the casting is it's going to tend to accelerate die failure. This is due to heat checking of the die. We'll put in an extra heat from the heavy section of the casting. And so again, this is kind of the heat checking shown here. Again, this die heat checked early because of the heavy section of the casting. And so the die is failing prematurely because of this problem. Now, all dies will eventually fail from thermal fatigue, but if we have some thick sections in the casting, it's putting in extra heat into that area, and so it's going to introduce die failure much earlier, again, than we would like. And again, ultimately, if I don't manage heavy sections in the casting, if I don't manage temperature in the die, I can get gross cracking. So whole chunks of the die can split in half, or we'll get major cracks in it. And obviously, this is something that we need to prevent. Now, we also need to be aware of thin sections in the die. We just talked about thin sections in the casting. We also need to be aware of thin sections in the die. It's not enough to worry about thick casting, thin casting, but thin areas of the die, these areas are going to heat more because they're not able to absorb the heat or transfer the heat. And so again, thin areas of the die will tend to get very hot and again give us premature failure due to heat checking. So as we talked about doing a thin section analysis on the casting, we can also do a thin section analysis on the die. What it shows here, we have thin sections between standoff bosses in the middle of the casting. And again, if we get thin sections of the die, that might be areas where we can get soldering, and that's kind of what we're showing here. Soldering is when the casting is sticking to the die. You can see it here on the casting. You see it here on the die and here on the die. It happens because the die gets too hot. And so again, if we have thin sections in the die, then we can't transfer the heat away. They tend to get much hotter, and those areas are going to be prone to this kind of soldering. And then we're going to get a scab kind of defect on the casting. So what we're seeing here is that we can control what's going on in the die with thermal management, and we'll just talk about that here for a couple of slides. In the last webinar, I talked about the fact that die steels tend to be a poor conductor in the heat, I should say. The die steel is a poor conductor of heat. And we can actually do a simple conductance analysis or resistance analysis. These are commonly done in heat transfer applications, and again, we can do it in die casting applications. And again, we can kind of work out how to get the heat out of the die. And so here we're kind of showing an example again of the poor conductance of the die steel. What we're showing here is the heat transfer coefficient against flow rate of water, and the light gray line is where we've got a cooling line right at the die surface. Obviously, in practice, we can't have a cooling line right at the die surface, but in a simulation, we can do this. And this kind of shows me how we're going to remove the most amount of heat possible. However, the dark gray line is when we have the same cooling line at 1 inch depth, and you can see that we're removing significantly less heat than optimal conditions. So what it means is that I want to get the cooling line as close to the die surface as possible to the feature that needs cooling. Now, I should emphasize that there are rules in die casting in terms of when designing dies, in terms of how close these lines should be to the die surface. So again, you can go to diecastingdesign.org, you can go to the NADCA books, but probably the best source of information, again, is go talk to your local die caster. And again, they'll be very familiar with this in terms of what they're comfortable with, and they'll be able to give you great information about that. So if we look at the die design here, here's an example of cooling lines. These are the blue lines showing here. You can see we're going from one side of the die to the other, through or across the cavity. And this is actually a poor cooling line arrangement, what we're showing here. And certainly simple heat transfer analysis would tell you that you're not going to be able to cool the center of the die. And so we tend to have in this case, we'd have a hot center of the die. When the die gets too hot, it's going to fail early, as we just talked about, from thermal fatigue, from heat checking, and also maybe we'll get soldering of the casting to the die in this area. So this is a much better design, putting the cooling lines directly across the cavity. And again, there's a lot of science that goes into the placement of cooling lines. And so you can look at the casting design, the die design. How am I going to get cooling into thick areas? If you've got thick areas of casting, how is the die caster going to be able to get that heat out? And there's other constraints we're going to have. We've got to avoid features in the die. We've got to avoid ejector pins. We've got to avoid bolt holes. And so we've really got to think about how we're going to get the heat out of whatever it is, the casting that you're going to design. Okay, so that leads us on to how to optimize geometry. The CAD geometry, we've gone through various concerns. We're going to be doing a lot of iterations to optimize the design of our casting. So the idea is, how should I order these items in my CAD program so the CAD program will be flexible enough to allow me to make these iterative changes. So this is the recommended approach. Certainly first, create the base geometry. This is unoptimized, but maybe close to the final die casting geometry. And the idea is just to get the base features into the design. Then you need to add the holes. These are the chord, the holes that are going to be cast into the casting. Then you can start thinking about the parting line in terms of where is the parting line going to be. Then you can add the draft and fillets we were talking about, and then add machining features. And this would then allow you to have a nice clean model that, for example, if you wanted to do FEA analysis on, obviously they're going to want to see what the final machine part looks like. If you're going to do casting simulation, though, in terms of how the cavity is going to fill and how it's going to solidify and where the porosity is going to be, then obviously you want the model with step 6 missed out. We want to see the design, obviously, of what's going to be cast if we're going to do a model or a simulation of the casting. Okay, so let's move on then and talk about assemblies. So let's talk about designing for assemblies. And obviously the goal here would be to reduce all components into one die casting. So one of the first things you might want to ask yourself when you design a die cast component is, what is this casting going to be attached to? Can I die cast those components as well? Can I combine multiple components into a single die casting? And that allows you to address concerns such as assembling to different metals. Should I be concerned? How am I going to attach? How am I going to mount? What are the required material properties? And so we'll talk about some of those things as we go on. But what we're showing here on the left-hand side is 2 stamp components that have been bolted together. But on the right-hand side, we've got 2 components that have been combined into a single die casting. And so obviously, instead of making 2 components, now you're making 1 component. And once these 2 are being combined into a single component, then the next question you should ask is, what are other components in the assembly? Can I combine some of these other parts into a single die casting? So here's a quick example. This is a zinc die casting made of Zamac 3, and this was originally 6 parts that was consolidated into a single die casting. And in the first webinar, I think I gave some examples where the automotive people had consolidated 20 or 30 separate parts into a single die casting. So obvious, tremendous cost-saving potential here. The one shown here had an 85% cost saving, and so despite the fact they were making a much more complicated die casting, they had to make a tool that was quite expensive. The cost payback on this complex tool was only 6 months. And so, again, that shows the strength of all casting processes, but certainly in this case, specifically die casting. The example I just showed actually was a casting. It had threaded fasteners cast into it. And then this slide, therefore, summarizes different methods you can use to join die casting. So we can use threaded fasteners, we can use cast inserts, self-cutting fasteners, we can die cast external threads. We'll talk about that in a minute. Interference fits. Generally, we only have limited use of crimping, stacking, swaging, things like that. And this is the limited ductility that conventional die castings have. Don't really have enough ductility for those kind of forming operations. But certainly recently die castings have been developed that have a lot more ductility, and this has led to the increase in use of crimping and these kind of techniques. And certainly with high integrity die casting processes, with semi-solid, with high vacuum, with squeeze, now we can weld more defects, while with conventional die castings generally we tend not to weld. Shown here are some general guidelines for threaded fasteners. I'm not going to go through all this. You're going to get a copy of the presentation, and so you can go back and look through this information if you're interested. But I wanted to make sure that you are aware of it. Again, it is available. Again, you can go to diecastingdesign.org, the NADCA product design book. Great sources for this kind of information. So let's talk a little bit about if you're thinking about putting inserts into a die casting. When would you do this? Generally when you exceed the capabilities that the die cast material itself can handle. So if you have a bolted arrangement and you're worried maybe you'll strip threads on the die casting, or you've got an assembly that's continuously bolted or unbolted, bolted or unbolted, then you can look at the use of inserts. And so inserts can help distribute the concentrated loads and also avoid abrasive wear. So keep in mind that steel inserts can be cast in place into the die casting, and generally economics is going to drive whether or not you use inserts. Obviously, if you're going to cast around a steel insert with the molten metal, you've got to place that insert into the casting mold before each shot, so it's going to slow down the die casting process. So again, you've got to kind of think of whether that's the best approach or not in terms of using cast inserts. One other thing you've got to think about with cast inserts is that you've got to avoid galvanic corrosion between the die casting and the inserted material. So again, you can talk to the insert suppliers. You can get guidelines in terms of what insert material to use with what die casting alloys. Die casting alloys are going to readily accept self-tapping screws, thread-forming screws, spring clips, stamp nuts, things like that. Again, follow the published literature for the recommended applications. One important point to think about is that self-tapping screws are going to form chips. That may not be acceptable in some cases. In electronic applications, you don't want little bits of metal flying around inside, so maybe in those kind of cases, thread-forming fasteners might be a better application. So let's talk again a little bit about casting threads. I alluded to this a little bit earlier. We can cast internal threads in place. It tends to be difficult. It's basically an ejection problem, so it's not that common. So generally we tend to only do external threads. And with as-cast threads, we tend to get flash on the parting line. So often what we do is that we put a flat on the thread at the parting line location. This allows a flash to be trimmed. So whether or not you do this depends really upon the application. If you've got sealing or you need sealing along the threads, obviously a flat on the parting line is not going to be a good application. But conversely, if you've got an electronic application where you need to avoid the flash we just talked about, again, then a flat at the parting line is more common for those kind of applications. Can we do interference fits? Yes. Yes, certainly we can do that with die casting. One caveat, we do need to watch out for stress corrosion cracking with magnesium alloys, no problems with zinc or aluminum alloys. So, other than that, follow the instructions from the interference fit manufacturer in terms of the best way to size the interference fit. There are some limited use of other attachment systems. For example, the BMW shock tower I talked about in the previous webinar. I think we talked about in the first webinar. That's actually punch riveted into the frame, and that's a pretty innovative high vacuum die casting. So the alloy has much more ductility than conventional die castings. However, in the future, it's more likely we're going to see these kinds of innovative methods of attaching die castings, including possibly, well, not certainly welding for high integrity die castings, again for squeeze casting, for semi-solid casting, for high vacuum die casting applications. Do keep in mind, as we just talked about, galvanic corrosion can be an issue for all die casting alloys. If we look at the electromotive series shown on the right-hand side here, you can see that aluminum, magnesium, zinc, these are all on the anodic side. All the die casting alloys are on the anodic side. So they are going to tend to corrode when we attach them to dissimilar metals such as steel. So let's talk a little bit about galvanic potentials. For galvanic corrosion, there's basically 4 things that you need. You need a conductive liquid, such as water is generally the conductive liquid. You need electrical contact, i.e. the dissimilar pieces need to be touching, and then you need 2 dissimilar metals. As we just talked about, the die casting alloys, the aluminum, zinc, magnesium, these are going to be the anodes, and so they're going to preferentially corrode. The cathode is going to be the steel bolt holding everything together. So if you can get one of these things, if you can take one of these things away, and generally it's the electrical contact, the parts in contact is taken away, then you can get rid of the galvanic cell and you get rid of the galvanic corrosion potential. So this is why we look at painting, taping, sealing compounds, anything that can keep the 2 pieces of the dissimilar metals from touching and corroding. So when we do run into problems, the best way to avoid galvanic corrosion is actually to paint the cathode. And so the cathode, as we talked about, is a steel piece, a steel bolt. So for example, if we're attaching 2 aluminum die castings together, we would paint the steel bolt. However, for consumer applications, generally that's not wanted. People want a painted part and an unpainted bolt so they can easily replace a bolt. So again, you need to be aware of those kind of concerns, the difference between the science and the consumer requirements. Now, there's a number of ways recently that engineers have worked out how to avoid galvanic corrosion. A lot of these have come through the large automotive initiatives, the US CAR, the USAMP initiative, and they've come up with certain ways, washer arrangements, and other approaches for avoiding galvanic corrosion. So again, if you're interested, go search out that kind of information. As we talked about previously, again, when we look at design features, we do need to worry about creep and relaxation, especially in zinc and magnesium castings, not so with aluminum castings. Aluminum castings tend not to be a problem. And then, as we talked about just previously, stress corrosion cracking for the magnesium alloys such as AZ91D. Let's talk a little bit about machining. It's relatively simple to machine die castings. However, obviously the whole point of die casting is it's a net shape process or a near net shape process. And so obviously we want to design the casting with the minimum amount of machining stock. Ultimate goal is don't machine at all. Machining tends to be expensive, so if we can avoid it, let's avoid it. So again, talking to the die caster ahead of time in terms of what can be cast and what has to be machined is going to be very helpful in terms of eliminating as much excessive finishing machining operations as possible. Now, if we look at the machinability of the die casting alloys, aluminum, magnesium, zinc, all these have good machinability. Of the 3, probably magnesium does tend to be the best. However, we've got to bear in mind, obviously, when machining magnesium alloy, we're going to produce magnesium chips, and so that can be a fire hazard in the plant. So again, just something to be aware of. Now, again, we can apply surface finishes to the die casting. We can do this for a whole range of different reasons. We can provide a decorative finish, protective barrier against oxidation or in the environment. We talked about filling, porosity, and any other small surface pits to prevent leaking. We can apply coatings to improve wear resistance, or as we just talked about, to insulate the dissimilar metals for galvanic corrosion. We can also treat the surface of the castings. There's a whole range of processes used, but probably blasting and vibratory feeding are the two most common. Obviously, the goal here is to end up with a uniform, bright surface finish on our castings. We can also use cast-in decorative surface finish. And so you can see here there's a range of different surface finishes. What we do is we apply this to the casting die, and then we make the castings. They replicate that surface, and so that gives us a nice textured surface on our die castings. Here's a decorative finish chart. Kind of shows us a range of different decorative finishes we can put on different alloys and where we might want to use them. For example, if we want to improve wear resistance for an aluminum die casting, then hard anodizing is a good way to go. Now, notice that for decorative finish that anodizing is not called out as a decorative finish, and the reason for this is that if you try to anodize or color anodize, for example, aluminum die castings, in fact, aluminum castings in general, you tend to get a blotchy finish. And the reason for this is that nearly all aluminum castings, die castings, and other casting processes are cast from aluminum silicon alloys, and we get a mixture of aluminum and silicon in the microstructure. The aluminum anodizes well, the silicon doesn't, and that's what gives us this blotchy finish. So generally, we don't do anodizing for decorative finish on aluminum die castings. Just as we've talked about designing, we also need to design for plating or platability if that's something we want to do. And again, on the NADCA website, we can get this information in terms of optimizing geometry, not just for the die casting itself, but also optimizing geometry for plating applications. If we want to talk about protection from atmospheric corrosion, all die casting alloys are very active and they're going to corrode faster than steel. But unlike steel, the die casting alloys are going to form a protective oxide coating. So while steel just continues to oxidize, the die casting alloys form this initial oxide layer that protects the remainder of the metal from further corrosion, and that's why we get no further corrosion. So all the alloys are actually quite good in atmospheric corrosion. If that's not sufficient, if you've got a really bad environment you need to put a casting into, then you can look at the type of coating shown here. Then the last thing I want to talk about then is prototyping of die castings. Prototyping die castings is quite difficult if we're looking at simulating functional performance. If we just want to shape, then that's easy, but if we're actually trying to work out how well the die casting will function in a certain performance, it's often difficult to capture all the aspects of the die casting. We have the skin effect, and then there's no other way to get the rapid cooling that we see on the surface of die casting. We can't truly capture this with other processes. We also can't capture the distribution of internal porosity. So we can't truly reproduce the mechanical properties, but we can do a good job if it's just shape or chemical composition that we want to do. But there are guidelines out there in terms of how to do this, and let's run through that quickly for each of the three classes of die casting alloys. So here with die castings, we can do it by gravity casting. Here's common gravity casting alloys, 356, 319, 390. And so depending upon the heat treatment shown here, we can get quite a range in mechanical properties. And so, for example, if we're looking at a die casting application that we're looking to prototype with a gravity casting, die casting normally is going to be around 20 KSI yield strength and about 3% elongation. So if we look at the 356 in the T51 temper, yield strength about 20, elongation slightly lower at 2% or so. So again, that's going to give you similar performance to a die casting, but again, it's not going to capture all the aspects of a die casting. If we look at magnesium, again, we can gravity cast AZ91D. We can capture many of the properties that are kind of shown here. A lot of properties are attainable, but some are difficult to match, including tensile strength, fatigue strength, and obviously, again, the porosity, soundness that we typically get with conventional die castings. Then finally, there's actually been quite a lot of work done on prototyping zinc and ZA alloys. And so the chart is shown here as obviously kind of a busy chart. I'm not going to go through all this again, but if you are interested in prototyping zinc die castings, go look at this chart in a bit more detail, and you'll kind of find out the best way in terms of doing that. Okay. So that's it for the whole 3 sets of the webinars. So let's just run through a few conclusions here before we take questions. So as we talked about at quite some length, die casting geometry should be optimized for the die casting process. We talked about draft, fillets, part inline, bosses, ribs, hole windows, symbols, and then uniform walls obviously being very critical. Part consolidation, that certainly should be a major effort in every die casting design. That's a huge potential way of reducing overall cost. We talked about the use of cast-in inserts if we want to improve the performance. Galvanic corrosion, if we've got 2 dissimilar metals, needs to be addressed. And then if we were looking at a prototype, die castings, there are ways to do that to get close to the performance, but again, you're not going to totally get the performance of die castings. So again, we've got time for questions. If you have any questions, please feel free to type them. Before we do that, again, let's go through the sponsors here. And one of the things, hopefully, that's really come out of this talk, these 3 webinars, is go talk to the your die caster. Certainly people that are new to designing die castings are probably not going to do a good job. We've given you a good introduction here, but there's a lot more information that the die casters know. And so go talk to them and have this iterative process going backwards and forwards, and you'll get a much higher quality casting out of the process by doing that. So again, Dayco, zinc die caster, Chicago white metal is aluminum, magnesium, zinc. Technical die casting, aluminum and zinc. Lakeside Solutions is zinc, and Somalax, aluminum, magnesium, zinc. So now it's time for questions. I'm not sure if Athena is with us today here or not. Normally she comes all along and tells us how to do questions.
I am.
Oh, then she can do it. Okay.
So there are a few ways that you can ask questions. Like Steve said, within the control panel, there's a text box. If you click within the text box, type your question in and hit submit, we'll get it in on our side. The next thing that you can do is you have a little hand icon. If you click on the hand, that just lets us know that you'd like to ask your question out loud. If you are doing that, please make sure that you are calling in on a phone or if you have a mic set up. Last but not least, you can always email us at webinars@diecasting.org and we will get your questions over to Steve. Again, that's webinars@diecasting.org. We can get your questions to Steve or send them to the appropriate person to answer or put you in contact with a die caster for your needs. There is one question that I saw come through that I can answer. Can we get a copy of the slides? Yes, you can. I will send those out probably first thing tomorrow, along with information on how to get the recording as well. And so with that, I'm going to pass that over to Steve and see if more questions come through.
Yeah, so please type your questions. Again, as we talked about at the beginning, I see there's one question, well, one technical question anyway. What is considered premature failure, how many cycles? Well, clearly it's dependent upon the alloy being cast. Zinc is the lowest melting temperature. Basically, the die is going to fail, or normally the die fails from heat checking, which is this thermal fatigue. Every time you make a casting, you heat the die, you eject the casting and spray the lube on it, it cools the die. So this heating, cooling gives us a tensile compressive load on the surface of the die, and ultimately it starts to crack. And depending upon your casting, if it's a real cosmetic part, then probably need to replace it at that time. If it's hidden away somewhere, castings, a lot of casters will allow, or a lot of customers will allow the caster to keep on casting for a while, but ultimately it's going to fail. So zinc is the lowest heat load on the die, so it lasts the longest, and I'm going to say 500,000 cycles, 500,000 shots, something like that. For aluminum, aluminum is the highest melting point and it's most aggressive on the die. And so it used to be, we would say, maybe now people are getting up to 200,000 shots as we use better steels and we understand the heat treatment, and also in terms of how to look after the steel with a good casting design. And so somewhere between that is kind of a good number for the life of an aluminum die casting die. How do we download the earlier presentations? Athena can come and tell you about that.
I was just sending a direct message. I'm going to send full download instructions to everybody for the 3 presentations. So.
I missed here. Can a die-cast part be welded to a? Oh, missed it. Can a die-cast be welded to a like material extrusion? Perhaps aluminum extrusion to the same material die-cast part. Well, a couple of things here. Firstly, if you have an aluminum extrusion and you have a die casting and you're trying to join them, why not make it a single die casting as we talked about earlier? I don't know whether that's a possibility. Obviously it's going to depend upon the constraints of the part. But obviously we just talked about the fact that if you've got a die casting and you're looking to join it to a aluminum extrusion, you can make it all into one die casting, and therefore you don't need to buy the aluminum extrusion anymore, and probably the die casting part is not going to change the cost hardly at all. So that's the first thing. Secondly, welding conventional die castings is a problem. This goes back to the porosity we talked about. We have entrapped gases in there. And when we weld it, you get a heat effective zone. This is an area that gets heated to very high temperatures, and we tend to get blistering of that part. So with a conventional die casting, no, you cannot weld it. But with a high integrity casting, a high vacuum die casting, a semi-solid casting, a squeeze casting, those tend to have much lower levels of entrapped gas, and so welding to those is much less of a problem. So if you want to weld to a die casting, you need to go with a high integrity type process. But again, why not make it all into a single die casting? Okay, so that's all I'm seeing so far in terms of questions.
Yes, that's all I see as well. So we'll just give it a couple more seconds here. If you're currently in the process of typing something in, if you would like to click that little hand icon, that just lets us know that you're typing and that we shouldn't end early. Steve, another question has come.
What is the residual height of the part in flash after trimming generally? That's an interesting question. I mean, if you do it correctly, it really should not be hardly anything at all. But I'm not sure that I have a good number for that. So again, I would go talk to your die caster. So rather than me kind of coming up with a number, but generally the whole point of trimming is that we're going to remove the flash and have a part that we don't need to finishing any other way. Maybe you can clean it up finally by by blasting it or by vibratory finishing. But the point is that then you don't need to remove it afterwards. But I'm not sure exactly how thick So again, go talk to a die caster. I'm not sure I should give an intelligent answer to that one.
All right, I don't see any more questions coming in. So with that, everybody, thank you for attending. And Steve, thank you for presenting. And again, feel free to reach out to us with any questions that you might have about the die casting process, and we will be happy to help you. So with that, thank you guys, and have a great rest of your day.
Thank you, everyone.